Okay, good afternoon, Brooks, I guess. I'm not sure everybody else is, but hopefully they'll start filtering in soon. I think my document camera is unplugged. I'll need just a second to get the doc cam plugged in and then we can get rolling. Today is an exciting day. I'm going to show you guys some really cool shit. Slot this in back here. There she goes. All right. Okay, good afternoon, lads and ladies. Today we're going to pick up where we left off last week. And if memory serves, we were just beginning to talk about dividing polynomials, which is a gloriously exciting topic. So I'm really stoked for today's lecture, and I hope that you guys enjoy it as well. Let's get this going. Your homework this week is fairly lengthy. I'll warn you at the start that that is the case. So I want to strongly encourage you to begin it right away. Let's see how this color shows up. That's a little faint, isn't it? Yeah, I will switch to a darker tone here. Not rhetorically, of course, but a literally darker color. What is that? Okay. Of course, right now my phone starts blowing up. So today what we're going to do, like I said, we're going to talk about dividing polynomials. And there's a few topics that are naturally linked to this. Factoring and graphs are, of course, linked to division of polynomials. Remember that factoring is essentially dividing. If you factor a number out of an expression, really you're dividing every number in that expression by whatever it is you're factoring out. So when we talk about division of polynomials, I'll do my best to connect that to what we were talking about last week, which was, of course, graphs, right? Graphing of polynomials and how the factors connect to the shape of the graph. If you don't remember, last week we spoke about polynomial end behavior and how the factors of a polynomial determine the shape of the graph near the roots associated with those factors. So you may want to right now, while I'm introducing this week, flip back through your notes from last Wednesday and take a look at that section, especially the section on local behavior near roots. That will be very intimately related to this. The other things that we're going to talk about this day are the fundamental theorem of algebra. And you know the word theorem is important in mathematics. Remember, a theorem is a true statement that we invoke again and again. So if you're talking about a fundamental theorem, then of course you're dealing with an extra important true statement. The fundamental theorem, again, is fundamental theorem of algebra. We're going to talk a little bit about complex numbers. And that's it for the most part. So the first thing we need to do is talk about division of polynomials. And there's two types of division, two kind of algorithms for dividing polynomials. One is called long division, and the other is called synthetic division. Oh, and I almost forgot a topic. This one is very important, the rational roots theorem. Okay, So the rational roots theorem, last week you may remember me hinting at some kind of important tricks for factoring. The rational roots theorem is your biggest tool for factoring large polynomials. I know everybody knows a lot of tricks for factoring. You know, factoring quadratics, you have the AC method. For factoring larger expressions, you can try to pull out any common terms, maybe factor by grouping. And then of course, yeah, the quadratic formula will find you the roots of any quadratic, so you can always factor any quadratic using those roots. But the rational roots theorem is really the best tool that exists for factoring larger polynomials, polynomials of degree 3, 4, 5, and so on. So this is a lot to go through. Let's go ahead and jump in. First, we're going to talk about how to divide polynomials. So it is a fact that given any two polynomials, P of x, and I'll call this one D of x. So you kind of think of it, we're going to start with the polynomial P and try to divide it by the polynomial D. We can always express P of x over D of x as some quotient polynomial plus some remainder polynomial over D of x. So here D is usually called the divisor, Q is usually called the quotient, and R is called the remainder. And there's a neat fact here where the degree of R of x is less than, could be 0, but it's less than or the degree of, let me think now, is less than the degree of the divisor. So I know I ran out of space here a little bit and my handwriting got a little sloppy. What this says is that the degree of the remainder polynomial, what I'm saying here, is that the degree of the remainder polynomial is always strictly less than the degree of the polynomial you're dividing by. Okay? So remember, degree is the largest power of x that shows up anywhere in the polynomial. What I'm saying is then if you give me some polynomial p and you want me to divide it by some other polynomial d, I can do that. There will always be, it'll always be possible to perform that division. The output when you perform that division will be firstly another polynomial, and then you'll have a term over here, which is the remainder over the polynomial divisor, the polynomial that you're trying to divide by. And the idea is that the remainder is always smaller than the divisor. So think of this as being a lot like the regular long division algorithm that you learned for numbers in 2nd grade. This says where 0 is less than or equal to the degree of R of x, and the degree of R of x is strictly less than the degree of D of x. So the degree of the remainder is always strictly less than the degree of the divisor. So this is analogous to this idea that, for example, if I wanted to take 25 and divide it by 7, well, 25 doesn't go evenly, 7 doesn't go evenly into 25, but 7 goes into 21, it goes in there 3 times, right? So 25 divided by 7 is a little bit bigger than 3. It's bigger by how much? Well, what's the remainder if you try to divide 25 by 7? 7 times 3 is 21. So the remainder is 4. So I could write 25 over 7 as 3 plus 4 over 7. So this is something that most of us learned how to do with numbers in elementary school, right? You try to divide 25 by 7, doesn't go evenly, but there's 3 copies of 7 in here in the form of 21. And so I can say, okay, 25 divided by 7 is equal to 3 plus the fraction 4/7. So this is kind of like your Q. This is like your R, and this is your D. The same thing that you can do with whole numbers, you can do with polynomials. There are special terms in abstract algebra for sets of objects where you can divide like this, and they're called Euclidean domains. This is called the Euclidean division algorithm. And if you want to study that, take a course called abstract algebra down the road. But for now, we want to learn how to do this. I give you a polynomial P and a divisor D, and I ask you to go ahead and divide P by D. So let's get some practice, shall we? First, questions on what's written here, I should say. Analogous to this process with whole numbers. Okay, so I'm going to show you long division first. I'm going to divide the polynomial P of x equals, and I'll just make something up. How about 4x cubed minus 4x squared plus 3x plus 6 by the polynomial d of x equals, we'll start with something simple like x minus 2. Okay, so I want to divide P by D. And the result, the output, should be another polynomial that I'll call Q. And then I should also have a remainder polynomial. Let's see how this goes. The way we do this is you write down the polynomial P. You draw your kind of division bar, your long division bar like you learned in elementary school for numbers. And then you write down the polynomial D over here. And then we look at just the lead term of P and just the lead term of D. And I ask, by what must I multiply this, just the lead term, in order to get this, just this lead term? So what do I need to multiply x by in order to get 4x cubed? Well, in order to turn x into 4x cubed, yeah, exactly, I need to multiply by 4x squared. So I write that up here. So that's our first step. You just look at the lead term here and the lead term here. You ask, what do I need to multiply this guy by in order to get this guy? The answer in this case, to get x to turn into 4x cubed, I need to multiply it by 4x squared. Your second step is to go ahead and multiply this guy by everything here. So 4x squared times x is 4x cubed. 4x squared times negative 2 is minus 8x squared. and then you subtract one row from the other row, and you have to subtract the whole row. So down here, I'm going to put the result of the subtraction. 4x cubed minus 4x cubed, that's 0. Negative 4x squared, so I'll even write it. So, well, no, I shouldn't write it, it'll clutter things. But then negative 4x squared minus negative 8x squared. What is that? Well, that's negative 4x squared minus minus makes plus 8x squared. That's a positive 4x squared. And then these guys just come down, right? Because I'm subtracting nothing from 3x. So I have plus 3x and plus 6. So again, I take this whole polynomial and I subtract this whole polynomial from it. The result goes here. That's one loop of the division algorithm. And now you just keep doing that. So sure, let's come back up here. My first step is to just write these guys like that. I say I'm going to divide this by this. I pay attention only to the lead terms. So here and here. I ask, what do I need to multiply this lead term by in order to turn it into this lead term? To turn x into 4x cubed, I need to multiply x by 4x squared. So I write that up there. Then I distribute this 4x squared over this guy. And I write the result down here. 4x squared times x is 4x cubed. That's by design. That's why we wrote the 4x squared up there. And then 4x squared times negative 2 is minus 8x squared. Once you've done that, you subtract this row from the row above. That gives me this. And that's it. You just run that loop until you're done. So let's try it on this next guy. I ask myself, by what must I multiply x in order to get 4x squared? Is this making sense, Fabrice? So I ask, just looking at the lead term, what do I need to multiply this guy by in order to turn him into this guy? So x times what equals 4x squared? Well, x times 4x equals 4x squared. So I write plus 4x up here. Then I take this and I distribute it here. So 4x times x is 4x squared. 4x times negative 2 is minus 8x. And then I'm going to subtract this row from this row. It's very similar to the long division algorithm for numbers. If you remember learning how to long divide in elementary school, this is very, very similar. If I subtract 4x squared from 4x squared, I get 0. 3x minus negative 8x is 3x plus 8x is 11x. And 6 minus nothing is 6. All right, that's one more loop of this algorithm.
Wait, I looked away for like 2 seconds. How'd you get it? How'd you get the negative 8x again on this other row?
So I take this guy, the number that I found to make the one lead term turn into the other lead term, and I distribute it everywhere here.
Okay.
So 4x times x is 4x squared. 4x times negative 2 is negative 8x.
Okay, got it. Thank you.
So each loop of the algorithm, I ask, what do I need to multiply this lead term by in order to turn it into this lead term? This time on the third loop, to turn x into 11x, I'd multiply by 11. So I write plus 11 up here. Then I take that number that I just wrote up here and I distribute it over this. 11 times x minus 2 is 11x minus 22. And now we subtract one row from the other. (11x minus 11x is 0, that's by design. 6 minus negative 22 is 6 plus 22 is 28. And now I'm done, because down here, there is no polynomial I can multiply x by in order to turn it into 28. Bye, sweetheart. Be safe. I love you. So since there is no polynomial I can multiply this lead term by in order to turn it into this lead term, I'm done. What we've just discovered is that if you take 4x cubed minus 4x squared plus 3x plus 6 and divide it by x minus 2, the result is, zoom out a little bit, when I take this polynomial and I divide it by this polynomial, I get this answer, 4x squared plus 4x plus 11 plus this remainder divided by this divisor. So this is the quotient polynomial, q of x. The remainder, so q of x is 4x squared plus 4x plus 11. The remainder here is a constant function. It's just the constant polynomial 28. And the divisor, of course, is x minus 2. So this is the game. This is the division algorithm. This is how you divide one polynomial by another. This would be your answer for this problem. There will be some problems where you can use a different method called synthetic division. And I'm going to show you that. And Lily, I think that's what you're asking. Can we use synthetic in place of long division? Sometimes yes, and sometimes no. The problem we just did is an example of a problem that can be solved using synthetic division. But synthetic division only works when the divisor polynomial is linear. So I will show you the synthetic division algorithm next. I'd like to take a second here though. Yes, there will be some questions that specify the method as well. Yeah. So we do need to be comfy with both methods. I'd like to take a second and clear up any questions that we have about this example. This is a nice example to get started with. Take a look at your notes, take a look at the work here, make sure everything is correct. You can think of kind of this block as being one step, and that one step gave us this guy. This block as being one step, and that block came from this guy. This block is one step, and this block came from this guy. Once the thing you get here has degree less than the degree of your divisor, you're done. So the degree of my divisor here, x minus 2, that's a degree 1 polynomial. So I know I'm done when I get a term here of degree 0. Constant is a polynomial of degree 0. Let's try another if there are no questions about this. First, again, I want to make sure we're comfy with this example. I'm going to do one more long division example, and then I will show you synthetic division. Synthetic division is a time saver, but it only works in certain cases. Ms. Constant, are we feeling a little bit more comfy? Are there any questions on this one? Okay, I am going to move to the next example then. In order to be charitable, I'll grab it from your homework this week. So this week's homework is right here. Let's pop it up. And let's do something where we're dividing by a polynomial of slightly larger degree. So I'll do number 8. They want us to find the quotient and the remainder. So this is homework 6, problem 8. Find q of x and r of x. This is x squared minus 5x. Oh wait, no, we wanted to do, yeah, the one below that. X to the 4 minus 4x cubed plus x minus 2 over x squared minus 6x plus 1. Okay, so in other words, here p of x is the numerator, x to the 4 minus 4x cubed. Sometimes it's useful to write in the x squared term here. You don't see any x squareds, do you? It goes from x cubed down to x. That means there's a plus 0x squared, and then plus x minus 2. The divisor polynomial, the thing I'm trying to divide by, is the quadratic downstairs, x squared minus 6x plus 1. So my goal is to long divide the polynomial p by the polynomial d and get out a quotient and a remainder term. So I'll set it up the same way. X squared minus 6x plus 1 is going to be dividing x to the 4 minus 4x cubed plus 0x squared plus x minus 2. Again, what we want to do is look at the lead term here and the lead term here. I ignore all the other terms except for the front term, the highest order term. By what polynomial must I multiply x squared in order to turn it into x to the 4? So this time, if we think about this, x squared times x squared is x to the 4. So yeah, here, my very first term in the quotient is x squared, because this times this is this. Now what I do is I go ahead and take this guy and I multiply it by everything here. I distribute x squared across the polynomial d. So x squared times x squared, that's x to the 4. X squared times negative 6x is negative 6x cubed. X squared times 1 is x squared. And then I take these two rows and I subtract. Oh, you're good, no stress. Do make sure it's written down correctly though. So x to the 4 minus x to the 4, that's 0. negative 4x cubed minus negative 6x cubed. That's negative 4x cubed plus 6x cubed. That's 2x cubed. 0x squared minus x squared is minus x squared. And these guys just come down. So that's plus x minus 2. That's one loop. I'm going to run that loop again. By what polynomial must I multiply x squared in order to turn it into 2x cubed? Well, that's 2x. Yeah, 2x times x squared is x cubed. Perfect. So up here, I write plus 2x. Ah, shit, my pen. Plus 2x, like that. And then I'm going to take this plus 2x and distribute it over this guy. So plus 2x times x squared is 2x cubed. That was by design. 2x times negative 6x is minus 12x squared. And plus 2x times 1 is plus 2x. And I subtract the bottom row from the top row. This minus this is 0. Negative x squared minus negative 12x squared is negative x squared minus minus makes plus 12x squared. So that's positive 11x squared. X minus 2x is negative x. And minus 2 minus nothing is minus 2. That's my second loop done. Finally, to turn x squared into 11x squared, I would need to multiply by 11. So plus 11 goes up here. Then I multiply every term here by this plus 11. So I'll have 11x squared. And then 11 times negative 6x is negative 66x. And 11 times 1 is 11. And I subtract the lower row from the upper row. 11x squared minus 11x squared is 0. Negative x minus negative 66x is negative x plus 66x, which is 65x. And negative 2 minus 11 is the negative of 2 plus 11 is negative 13. And now I'm done, because the degree of the thing here is less than the degree of the thing here. So there is no polynomial term I could multiply x squared by in order to turn it into 65x. That's what tells me I'm done. And all of this work has shown that x to the 4 minus 4x cubed plus x minus 2 divided by x squared minus 6x plus 1 is equal to this quotient, x squared plus 2x plus 11, plus this remainder over this divisor. In other words, q of x is x squared plus 2x plus 11, and r of x is 65x minus 13. Cool stuff, right? There's lots of reasons why you might want to do this. One of the coolest is something called the remainder theorem. But before I show you that theorem, I want to show you a shortcut for certain division problems. And for my first example, I'm going to return to our first long division example. Before I do that, any questions on this long division process? We've seen 2 examples now. It seems like we're mostly getting comfy. Any questions about what we're doing here or how we're using it to write this and conclude these?
I have a question.
Please, yes.
Is it always positive on top? You know, when you're before distributing, is it always positive?
On top of what?
The first division, you know, on top, the very top.
Here?
Yes. Is it always positive?
No, sometimes you'll find a negative number here. Like if this had come out to negative 2x cubed, then to get x squared to turn into negative 2x cubed, I would need to multiply by a negative 2x. So the sign here comes from that question about the lead terms. It's just the case that in the 2 examples we've seen, the quotient always had positive coefficients.
Thank you.
So good question. Any other questions? Okay. One thing that you may start to notice as you solve these long division problems is that really all the addition, subtraction, and multiplication work we're doing throughout this depends on the coefficients, the numbers that are in front of each power of x. And one way to speed this process up is to arrange those numbers into a certain, we call it matrix or grid, array, table, such that you don't have to write the x's, you can just write the numbers and then run the same sort of loop. That is called synthetic division. So I'm going to return to this first problem we did. And show you a quicker way to proceed. I can begin just by writing down the coefficients of P. And then over here, I'll write down the number that makes this 0. So x minus 2 is equal to 0 when x is equal to 2. In other words, you write down the root associated with the factor that you're dividing by. And then I like to put this guy in. So this is called synthetic division. You begin by bringing this number down. Then you multiply this number with this number. 2 times 4 is 8, and you write that over here. Then you add these up. Negative 4 plus 8 is positive 4. You write that here on the same row as the number you brought down. That's why we scoot this guy all the way down here. Then you do the same thing. You multiply this times this and write it here. So 4 times 2 is positive 8 again. And you add these. 8 and 3 is 11. Then you multiply this and this. 2 times 11 is 22. Add those up. 22 plus 6 is 28. compare this to what we got here. Does anybody recognize some things that look the same? Four, 4, 11.
The remainder and all the
4,
leave.
4, 11. And yeah, the remainder was 28. So the way this synthetic division works, this last term here will be your remainder. And these will be the coefficients of the polynomial q of x. Remember what you're doing here. You're dividing a polynomial of degree 3 by a polynomial of degree 1. So the quotient will always be a polynomial of degree 2. You take a cubic and you divide it by a linear polynomial. A 3 thing divided by a 1 thing will always give a 2 thing. In other words, the quotient polynomial dividing a polynomial p of x by a degree 1 polynomial d of x, dividing a polynomial p of x, will always yield a quotient polynomial of degree 1 less than the degree of p. I should say of p of x, just to be consistent with the notation. So like you divide x to the 5 by x, you get x to the 4. The same thing is true for more complicated polynomials. You divide something that starts with an x cubed by something that starts with an x, and you'll get something that starts with an x squared. So this is going to be 4x squared plus 4x plus 11. Just from the synthetic division, I know that these are the coefficients of the quotient, and I know that the quotient has to be of degree 2. So this is the number that goes in front of x squared. This is the number that goes in front of x, and this is the constant. And the remainder here is a constant function, 28. So we get the same result that we got using long division, but we get it faster and with less writing here. So synthetic division's dope. It's nice, it's quick, it's easy. But it only works if the thing you're trying to divide by looks like this. X minus something. You put the something here, you put the coefficients of p of x here, you bring down the first number, multiply, write that here, then add those. Multiply, write that here, then add those. Multiply, write the result here, then add those. Once you're done, this will always be your remainder, and this will always be the coefficients of the quotient. Remembering that the quotient is always degree 1 less than the degree of the original polynomial p. How do we feel about this synthetic division?
Pretty good.
I like it. I'm a big fan. And yeah, Lily, you're exactly correct. That's where I was going to go. So d of x must be a polynomial of the form x minus c. That's the only time you can use synthetic division. So the question I was going to ask is, could we have used synthetic division on the second example here? And the answer is no. We could not have done this guy with synthetic division. We had to use long division because the thing I'm trying to divide by is not degree 1. It's not x minus 5 or x plus 2. It's got an x squared in it. So we have to use long division there. So I use synthetic division a lot when I solve the sort of problems we're looking at. You'll see me use it a lot, but there are some cases where we cannot use it, like this. Now I want to introduce you to that theorem. So this is called the remainder theorem. And it's super cool. You know, sometimes in a problem, you have to plug a number into a big complicated polynomial, right? Like you got to plug 5 into some huge polynomial. And that's a pain in the ass because you got to, you have to raise it to these powers and then sometimes have a common denominator and lots of arithmetic to do. The remainders theorem says that for any polynomial p of x and any number c, p of c, the thing you get out by plugging in c for x in p of x, is equal to the remainder when p of x is divided by x minus c. This is super duper cool. The proof isn't very hard. I'm going to show you the proof. This is the first proof we've done together, I believe. So let me show you. Proof is what mathematics is really all about. Mathematicians do not spend their time doing computation. We try to prove theorems. Proof. We know that for any polynomial p, we can write p of x over x minus c equals some quotient q of x plus r over x minus c, where r is a constant. How do I know that r is a constant in this setting? The remainder isn't always a constant. We saw that on the second example we did. The remainder there was not constant. It was a linear function. So what is it about the setting that I'm working in now with this proof that tells me r is a constant? I'm just writing this down where d, the polynomial d of x, is x minus c. And the magic is that the degree of the remainder is always guaranteed to be less than the degree of the divisor. Here, the degree of the divisor, d of x, the degree of this polynomial, x minus c, is 1. So I'm guaranteed that the degree of the remainder, r, is less than 1. Well, the only polynomials that have degree less than 1 are constant functions. So r here has to be a constant. This implies if you multiply both sides everywhere by x minus c, that p of x is equal to x minus c times q of x plus x minus c times r over x minus c. Well, r over x minus c, I can cancel these factors, and I find that p of x is equal to x minus c times q of x plus r. And now we're almost done with the proof. If I plug in c for x, we get that p of c is equal to c minus c times q of c plus r. But c minus c is 0, so this is 0 times q of c plus r. And 0 times anything is 0, so this is 0 plus r, which is just r. So p of c, the output from the polynomial p of x when you plug in x equals c, is r, where r is the remainder when p of x is divided by x minus c. That's the end of the proof. And it's a beautiful theorem that can save you lots and lots of time. It doesn't matter how you do the division, because here you're dividing by x minus c. You could do it long ways, or you could do it synthetic ways. Either way, the remainder is always equal to p of c. I'm going to show you an example where I make use of this theorem, and then I'm going to start showing you how to factor big-ass polynomials. I'll give you just a second more if you're writing. This theorem can be a good source of fun exam problems, tricky problems. So I want to make sure that everybody's comfortable with the statement of the theorem. Are there any questions about the statement of the theorem?
What would the C be?
Any number, whatever number you want. So if you wanted to plug in 5 or 1/2 or pi to a polynomial, you can divide that polynomial by 5 or 1/2 or whatever, or by x minus 5 or x minus 1/2 or whatever. Calculate the remainder. That remainder is what you would have gotten if you plugged that number into the polynomial. So sometimes plugging a number into a polynomial is hard. And division can be done very quickly using synthetic division. So sometimes rather than plugging a number into your polynomial and simplifying everything, it's much, much faster to do the synthetic division and calculate the remainder. According to this theorem, the remainder is always the same thing that you would have gotten if you plugged that number into the polynomial. So instead of plugging in, calculate the remainder.
But would the number C be given in the problem, or like
Yes, it would.
Okay.
So let me grab one from your homework. There's a few problems in here that ask you to do this. Remainder theorem. So let's look at, did I only give you 2? I'm going to look at number 10, but I'm going to make it a little more challenging. I'm going to use, actually, let's do number 11, and let me use c equals 1/2. So I'll write this down. This is similar to homework 6, number 11. Find P of 1/2, where P of x is, and I'll use their P of x cubed minus x squared plus x plus 4. X cubed minus x squared plus x plus 4. So if I wanted to find P of 1/2, I would have to plug in 1/2 for x everywhere. This would be, God damn it, come on, focus. This would be 1/8 minus 1/4 plus 1/2 plus 4. And then I would have to have a common denominator among all of those things. That's a pain in the ass. And I would have to do a whole bunch of kind of nasty arithmetic. But instead, I can synthetic divide. The coefficients here are 1, -1, 1, and 4. I bring this down. 1/2 times 1 is 1/2. I add. -1 plus 1/2 is -1/2. Multiply. 1/2 times -1/2 is -1/4. Add. 1 plus -1/4 is 3/4. 1/2 times 3/4 is 3/8. And I add, and this is the only slightly tricky part, 4 is 16/8. 16/8 plus 3/8 is 19/8. So I've learned a bunch of things. First, here's my remainder. So I've learned that P of 1/2 is equal to 19/8. And I never even had to plug 1/2 into this polynomial. My theorem just gives it for free. I also learned, so that's the solution to the problem, right? Let me be clear about that. This is what we were asked to find. And we're able to do it without ever plugging in. It's awesome. Also, we learned, I know, right? Yeah, I feel the same way, Ronald. I think that this is like shocking and useful. It saves you so much time. Also, we learned that if you take P of x, x cubed minus x squared plus x plus 4, and you divide it by x minus 1/2, that the quotient polynomial, remember the degree should be 1 less than the degree of p. The degree of p is 3. So the quotient polynomial is 1x squared minus 1/2 x plus 3/4 plus my remainder, 19/8, divided by x minus 1/2. So you have a few problems in your homework that ask you to use this theorem to evaluate a polynomial at a certain number. And the advantage to doing that is just that it can save time because synthetic division is so fast. Another consequence of this theorem is that x minus c is a factor of p of x if and only if the remainder when p of x is divided by x minus c is 0. This makes intuitive sense. When I say something is a factor of something else, that means that the first thing goes neatly into the second thing, which is the same as saying that when you try to divide, the remainder is 0. Why is this true? Well, if the remainder when you divide p of x by x minus c is 0, this is a c, not a 0, that means that P of C is 0. And we learned last Wednesday that P of C is 0, i.e. C is a root for P of X, can only be true if X minus C is a factor. Remember, that was the factor theorem that we talked about last Wednesday. So one way to test whether or not something is a factor of your polynomial is to try and divide by that thing. If the remainder comes out to 0, then you found a factor. Since factors correspond to roots, you've also found a root. And this is the main tool that we use when we want to invoke our main theorem for factoring big polynomials. We come up with a list of possible roots. And then you attempt to divide by each of the corresponding factors. Once you find a guy whose remainder is 0, you know that you've found a root, which means you must have also found a factor. So the next thing I would like to show you is the rational roots theorem. Make sure I'm not skipping over anything. Yeah, rational roots theorem is next. First, any questions on what I did in this problem? Okay. So the next thing I want to do is show you the rational roots theorem, aka rational zeros theorem, and use it to factor some polynomials that before now we couldn't factor. This theorem looks a little bit intimidating when you write it down, and it is indeed a little bit intimidating to use. So I want you to focus extra hard here for a second. Make sure you take nice, good notes on this. This says if the polynomial P of X has any rational roots, then those roots must be of the form plus or minus P over Q. So I want to be clear here. The polynomial is a big P. This is a little p, little q. So not the same symbols there. Where P, little p, is a divisor of the constant term and Q is a divisor of the lead coefficient. What this theorem does is it gives us a tool, or it gives us a list of possible rational roots. It gives us a list of numbers that we can check. We check using synthetic division. Once we find an element from our list that gives us a remainder of 0, we know that x minus that number must be a factor of your polynomial. And also, the synthetic division will give you the quotient. Knowing those two things, you can extract a factor from your polynomial, reducing the degree by 1. Then you try to factor what's left over. So this is a tool for factoring big polynomials. I'm going to grab an example problem here from your homework where we can use this to factor a big polynomial. So there's a handful of problems in your homework that are similar to the ones from last week, where I give you a graph or a list of roots, and I tell you to write down a polynomial with the appropriate degree. These I don't think you'll have a hard time with. You just have to remember the local behavior near the roots, like a cross or a bounce. But this is a good fellow. Or let's start with this. So I want to find all the roots and factor this polynomial. The problem just says to find the roots, but I want to find the roots and factor. So I'll say, for example, factor the polynomial p of x equals 4x cubed minus 10x squared plus 9. Until now, we didn't have a tool to factor polynomials like this. I know in college algebra or in high school, you learned how to factor quadratics, but this is not a quadratic, it's a cubic polynomial, cubic for degree 3. So since there isn't a common factor of x that I can pull out of everything, there isn't any common number that I can factor out from everything, and the degree of the polynomial is bigger than 2, before today, you guys didn't know how to factor this. So what we're going to do is employ this rational roots theorem. He tells me that if this thing has any rational roots, they must be of the form plus or minus a divisor of 9 divided by a divisor of 4. So here's how I like to do this. I say I'm going to use the rational roots theorem, and then I write down my list of p's and q's. The possible values of p, remember these are divisors of the constant term. Well, what numbers divide 9? 1, 3, and 9. Similarly, I write down a list of divisors of the lead coefficient. Here the lead coefficient is 4. What kind of numbers divide 4? Well, just 1, 2, and 4. Therefore, the possible rational roots, and remember what rational means. It means a ratio of whole numbers. So not like the square root of 2 and not like I, just nice roots. Possible nice roots are plus or minus p over q, where p comes from this list and q comes from this list. So that could be plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. That's all the possible guys with p equal to 1. Then I've got plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4. And I continue my list down here. So that's all the guys I could come up with whose numerator is 1. All the guys I could come up with whose numerator is 3. And now I'll use all the guys I could come up with whose numerator is 9. So that's plus or minus 9 over 1, plus or minus 9 over 2, plus or minus 9 over 4. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different things that I would have to check using synthetic division. This is what I mean when I say the theorem can be kind of hard to use. The theorem generates a large list, and now you have to go in and check each one. You don't have to check every single number. You start here, and then you check until you find a guy that works. Once you find a guy that works, you get new information out of that. You're able to extract a factor. So I always start with the easier ones. It's more than 9, right? It's 18, because each one of these you have to take with a possible plus or a minus. So it's tiresome to check all of them. But so the p's, remember, is coming from the theorem. My p's are always divisors of the constant term. So here the constant term was 9. And I have to list all the divisors. Those are numbers that cleanly divide 9. So the numbers that cleanly divide 9 are 9 itself, 3, and 1. And similarly, Q has to be a divisor of the lead coefficient. The lead coefficient here is 4. So my possible Q's are 4 itself, 2, and 1. Those are all the positive integers that divide 4. So this gives me my list of possible rational roots. And then to find out which ones are actually roots and which ones are not, I use synthetic division. So I'm going to start by checking 1. And so I write 1, and then I write the coefficients of p. You have to watch out. There's a missing term here, right? There's an x term that's missing. So I have to insert that as a 0. P of x here is really 4x cubed minus 10x squared plus 0x plus 9. Just like you saw me do when we did the long division. When you do synthetic division, it's even more important that you remember to insert any missing terms as a 0 coefficient. So here's the thing I'm trying to divide by, x minus 1. And over here, I'll list the coefficients of p, which are 4, -10, 0, and 9. So here's my first little bit of synthetic division. I'll bring the 4 down. 1 times 4 is 4. -10 plus 4, that's -6. 1 times -6 is -6. 0 plus -6 is -6. 1 times -6 is -6. -6 plus 9 is +3. So is 1 a root of the polynomial p of x? Yes or no? Remember what our remainder theorem says. It says that p of 1 is the remainder when you divide p of x by x minus 1. So here, what's my remainder?
3.
And what would my remainder be if 1 was a root? It would be 0. Because p of 1 would be 0. That's the definition of a root, remember. A root is an x-intercept. It's a number you plug in for x that makes the whole thing 0. Here, I just learned that if I plug in 1, the whole thing would be equal to 3. You can check that easily, right? If you plug 1 in here, you get 4 minus 10 plus 9. That is 3. Good, yeah, exactly. So what we do is we start running through this list using synthetic division until we find somebody whose remainder is 0. 1 did not work. Let's try -1.
How come you're not using the entire P over Q?
No, I don't. I'm just doing synthetic division rather than writing P over Q. Or I'm sorry, maybe I don't understand the question. Could you be a little more specific, Ron?
Yeah, I just like blanked out. I forgot where you got that, like the divisor from. Like where are you getting it from right now?
Oh, so for P's, those are all divisors of the constant term.
Oh, okay.
And the Q's are all the divisors of the lead coefficient. And then for this list, I take every possible ratio, something from the P list over something from the Q list with the plus or the minus.
Okay.
So I'm going to check -1 next. I'll bring down the 4, multiply by -1, that's -4. -10 plus -4 is -14. -14 times -1 is +14. 0 plus +14 is 14. 14 times -1 is -14. -14 plus 9 is -5. So P of -1 is -5, not 0. So neither 1 nor -1 are roots. I can cross them off my list. And we're going to continue like this until we find somebody who works. So my next move is to test 1/2. All right, 1/2, and then 4, -10, 0, and 9. Bring down the 4. 4 times 1/2 is 2. -10 plus 2 is -8. -8 times 1/2 is -4. -4 plus 0 is -4. -4 times 1/2 is -2. -2 plus 9 is +7. So P of 1/2 is 7. Again, not 0. So I try something else. -1/2. Write the coefficients. Bring down the 4. -1/2 times 4 is -2. -10 plus -2 is -12. -12 times -1/2 is +6. 0 plus +6 is +6. +6 times -1/2 is -3. -3 plus 9 is +6 again. So neither of the 1/2s work. We can rule them out. So my next move would be to check the 1/4. Same sort of game. 1/4, 4, -10, 0, and 9. Bring it down, multiply by 1/4, that's 1. -10 plus 1 is -9, times 1/4 is -9/4. 0 plus -9/4 is -9/4. -9/4 times 1/4 is -9/16. +9 minus 9/16 is definitely not 0. And I'm not even going to bother calculating it because I know it's not 0. And that's really all I care about. So I know +1/4 doesn't work. Let's try -1/4. Bring this down. -1, -10 and -1 is -11. It's going to be +11/4 plus 0 is 11/4. So it'll be -11/16. And when I add 9 and 11/16, I know I'm not going to get 0. So again, I won't waste time computing it. I just move on. Neither positive 1/4 nor negative 1/4 work. So next I move to 3/1, which is 3. Bring down the 4. 3 times 4 is 12. Negative 10 plus positive 12 is positive 2. 3 times 2 is 6. 6 plus 0 is 6. 3 times 6 is 18. 18 and 9 is 27. Again, not 0. This kind of looked like it had promise, though. Something about the 3 upstairs and the 4 downstairs both looked promising through this process. So I'm starting to suspect 3/2 or 3/4. And we could jump to one of those, but just to show you what this looks like, I'm going to go through it until we find one. So you get a feel for what this algorithm is like and how it can be kind of tedious. Bring down the 4, negative 12. Negative 10 and negative 12 is negative 22 times negative 3 is positive 66. This is running away pretty quickly. 66 times negative 3 is 180 plus 18, 198. And 198 and 9, definitely not 0. It would be 188 or 189, negative 189. We have to go until we find one that does work. We have to go, Fabrice, until we find one whose remainder is 0. Once we get that, we can stop. And I'll show you what to do. Okay, so plus 3 and minus 3 are both out. Let's try 3/2. Bring down the 4. 3/2 times 4 is 3 times 2 is 6. Negative 10 plus 6 is negative 4. 3/2 times negative 4 is negative 6. This looks promising. 0 plus negative 6 is negative 6. 3/2 times negative 6, what's that? Well, you can cancel the 2. This is negative 3 times 2. So the 2's cancel. You get 3 times negative 3. That's negative 9. Oh, shit. 9 plus negative 9 is 0. Hallelujah. So here we are. We finally found one that works. Thank God. We just learned that x equals 3/2 is a root of the polynomial p of x equals 4x cubed minus 10x squared plus 0x plus 9. What's more, we learned the quotient. Also, we learned that 4x cubed minus 10x squared plus 9 divided by x minus 3/2 is equal to, here's your quotient, right? The degree of the quotient will be 2 because I'm dividing a cubic by linear. So that'll be 4x squared minus 4x minus 6. Here's the good news. We no longer have to continue searching like this because if you multiply both sides of this expression by x minus 3/2, you get 4x cubed minus 10x squared plus 9 equals x minus 3/2 times 4x squared minus 4x minus 6. So in other words, I was told I want to factor this thing. This looks like a step in the right direction, doesn't it? I factored it a little bit. I was able to, I use the word extract this factor from this polynomial, and I learned that what's left over is this. And this is a quadratic now, so I can factor this using whatever tricks you remember for factoring quadratics. Every term there is divisible by 2. So this is x minus 3/2 times 2 times 2x squared minus 2x minus 3. So once you find, using synthetic division, a number that is a root, i.e. a number that yields a remainder 0, you stop the synthetic division and you write down the quotient. You write down your polynomial divided by x minus that number which worked equals whatever quotient you get from these coefficients. Then cross multiply to get rid of this denominator, and you'll get your polynomial equals some factor times that quotient. And then your goal is to factor the quotient. You want to factor this all the way down. So once you find 1, 0, you don't have to check all the others. That's the beauty. Once you find 1, 0, the degree of the polynomial you're trying to factor will go down by 1 because you'll have extracted a factor. And then you can start back over on this new polynomial. And this new polynomial will always be easier to factor than the one you began with because it will always be degree 1 less. So if you're unlucky, the polynomial you get in this step will still be large, like degree 3, 4, 5. Then you would generate a new list of p's and q's and start this process over for this polynomial. But here we're lucky. This is a degree 2 polynomial. I know how to factor those without using shit like this. So before you go back and start working on more synthetic division with this guy, you should ask yourself, is there anything I can do to factor him? The first thing I see with this guy is that I can pull out a 2. 4, 4, and 6, those are all divisible by 2. That gives me this. This polynomial, I can try to factor using the AC method. If I can't do that, I can use the quadratic formula. So let's see. If I want to factor 2x squared minus 2x minus 3, I use my AC method. I need to come up with 2 numbers, just a few, Austin, that multiply to 2 times 3, or multiply to 2 times negative 3, multiply to negative 6, and add up to negative 2. Can we think of any 2 such numbers? Numbers that multiply to 6, so that's got to be like 1 and 6 or 3 and 2. Those are the only possibilities, right? Well, 1 and 6 don't add up to negative 2 no matter how you take the signs. 3 and 2 don't add up to negative 2 no matter how you take the signs. So for this guy, I need the quadratic formula. So his roots are x equals negative b, that's positive 2, plus or minus the square root of b squared, that's 4, minus 4 times a times c, 4 times 2 times negative 3, all over 2a, which is 4. So that's 2 plus or minus the square root of 4 minus, let's see, this is 4 times negative 3, that's 12, times 2 is 24, and minus minus makes plus. So this will be 4 plus 24 all over 4, which is 2 plus the square root of 28 over 2, plus or minus the square root of 20, so over 4. So this guy has 2 roots. This guy can be factored as x minus 2 plus root 28 over 4 times x minus 2 minus root 28 over 4. Which means that my whole polynomial can be rewritten as 4x cubed minus 10x squared plus 9 equals, I'll put the number out front, 2 times x minus 3 halves times this quadratic, which factors like this. X minus 2 plus root 28 over 4 times x minus 2 minus root 28 over 4. And that is the fully factored form of this polynomial. I know it's not fast, but you should take a minute to appreciate how powerful it is. Factoring large polynomials is not an easy thing to do at all. It's very hard. In fact, there was a man named Évariste Galois, who in the year before the French Revolution proved that there's no way to come up with a formula for the roots, these numbers, of a polynomial degree 5 or greater in terms of the coefficients. So this rational roots theorem is the closest thing we have to an ultimate factoring tool. It gives you a list of things to check. You check them one at a time with synthetic division. Eventually, you will get down to something like this, where you've got some linear factors and some quadratic. If you're lucky, this quadratic will factor nice and easily. If you're unlucky, you'll need to use the quadratic formula. Here we were unlucky. We had to check quite a few things with synthetic division before we found this. And then we needed the quadratic formula for this. But nevertheless, we persevered. Here is our fully factored form. You could leave it like this, or if you wanted to, you could distribute the 2 across this guy. But you don't have to. And certainly you don't want to multiply all of this back out. Remember, our goal was to factor. This is fully factored. This is as nice as you could possibly hope for. You've got your lead coefficient, and then all of the factors in terms of the roots. So this statement right here is what we were trying to get to. This is as nice as it gets. Yeah, the goal is to get to here. Okay. So you've seen a pretty hairy example. This is about as tough as these get. Sometimes though, when you get a quadratic like this, the roots won't be real numbers. They'll be complex numbers. You can still do this same thing. The last thing I want to show you today, and let me see if we still have time. How are we doing? Oh no, we're over time. All right, so I'm gonna have to stop it here. We'll pick it up here on Wednesday, where I will talk about the fundamental theorem of algebra, which is cool shit. But you do now have all the tools you need to finish all the homework questions on polynomials. So all of this stuff where you're picking the graph, you need to first factor this polynomial all the way down using the tricks I just showed you. And then remember what we talked about last time. This root right here is coming from a multiplicity 3 factor because it has that S shape. And this root right here is coming from a multiplicity 1 factor because it crosses and it doesn't have that S shape. So these games where you have to factor the polynomial, then select the graph, your first step is always to do this, factor the polynomial. And then you'll use what we talked about last week to pick the graph. Right here, you see a root of multiplicity 2. So that's coming from something like x plus 3 times x plus 3, or x plus 3 quantity squared. All right, so get cracking on this homework. There is quite a lot of it. You want to finish up as much of the polynomial stuff as you can today. Yep, yeah, multiplicity too just means bouncing, or even multiplicity in general means bouncing. It can bounce positive to positive or negative to negative. Okay, so next time I'll pick it up from here. I'll do one or two more problems like these, and then we're going to start talking about these guys, rational functions. We'll talk about how to graph them, how to find their asymptotes, how to find their intercepts, all that good stuff. And we'll view them through the lens of what we've been doing with polynomials. After that, we'll be done for the week, but I'm going to try to prime you for rational inequalities. And then we'll be moving on to other types of functions. So again, get cracking on this homework. There's plenty of it. It's going to take you a while. If you have questions, come visit me in office hours, including questions about the test, any of that stuff. And I will see you guys on Wednesday. All right, take care.